Okay, hello everyone. Well, it's fun to be here. Long ago, I thought, wouldn't it be great if there was a museum of mathematics somewhere, sometime, someplace? That was probably 30 years ago. About a dozen years ago, the people who created MoMath, I came into contact with, and they said, we're actually going to make a museum of mathematics. So I was excited to be involved with that effort and to see MoMath, the physical National Museum of Mathematics, come into existence in 2012. So a number of years ago, MoMath was talking about what's MoMath 2.0 going to be like? What kinds of things should we think about having to expand on the material that's in the current Museum of Mathematics? And one of the areas that I had long been interested in was history of mathematics. And the question was, could we create some kind of gallery about the history of mathematics? And that has, a couple of years ago, we started to collect material that hopefully will build towards eventually having a physical place where the history of mathematics can be seen and celebrated right in New York City. But for right now, we've created a virtual gallery about history of mathematics, and I wanted to show you some of what's been created there here tonight. And this has been created by people at our company, Wolfram Research. The lead curators who are with us here tonight are Eric Weinstein and Bernat Espigdale. And this was funded by the Overdeck Family Foundation. And this is kind of the first public viewing of our virtual gallery. A virtual gallery, of course, also translates into just being a website. And you can go to that website and interact with the things that are there. And our goal was to try and identify some of the notable artifacts that have defined the history of mathematics, and to kind of make a bridge between those artifacts from often far in the past and our current understanding of mathematics and our current ability to do mathematics computationally and to deliver those kinds of things in a virtual web environment. So you'll see kind of a link between the ancient past and the current and future of mathematics here. So I should say a little bit about kind of why is the history of mathematics interesting? You know, I think the thing to understand about mathematics as an enterprise is it's basically the single largest and greatest intellectual artifact that our civilization has created. It's something people have been working to build what is now mathematics for about 4,000 years. And it's been an area where progressively over the course of time, more and more pieces have been being assembled that turn into mathematics as it is today. So when people learn math in school, whatever else, they're learning this long intellectual tradition. And it's kind of interesting because everything we know, everything we do now in math had to be discovered or invented by somebody sometime. And it's interesting to try and see how those inventions and discoveries happened. And it's also, I find it useful in terms of understanding, having a deeper understanding of the mathematics that we think about today and things where we say, it's obvious it works this or that way. Well, it wasn't obvious back a few thousand years ago. And it's interesting to see how people got to the understanding that we have today, and sometimes to realize that, well, there are other understandings that could have been had or that could even be relevant to have today. So, well, let me show you a little bit of our actual website here. So this is historyofmathematics.org, and this is our virtual gallery. So the idea is that there are different parts of this virtual gallery that concentrate on some of the different areas of mathematics that one might have heard about, like arithmetic and algebra and geometry and the Pythagorean theorem and primes and pi and polyhedra, and also mathematics education. And in each case, think of this as a virtual version of actual exposure to these artifacts. And I think one thing that's a good place to start is to kind of see, when we look back at the mathematics we have today, where did it originate? Can we see what it looked like when it originated? And a lot of the mathematics we have today originated, we know it existed in ancient Babylon, maybe 4,000 years ago. Babylon, what's now Iraq, was I guess the New York City of its time, the kind of meeting place and melting pot of lots of different cultures, and the kind of the top city of its time. So Babylon was also the place in the civilization where the idea of cities really got launched. And with the idea of cities came the need to kind of organize things more systematically. And with that need to organize things more systematically came the need to actually define how big was that plot of land? How much did that barley weigh? To do things that involved quantitative calculations to basically invent the things that turned into mathematics. So ancient Babylon and the need to kind of have things organized for the sake of having a city and having people operate in that city was kind of a driver of a lot of mathematics as it exists today. So let's take a look. Let's see if we can look at one of these artifacts here. So let's go to the geometry piece here, and we'll see a variety of different exhibits. This is Babylonian Geometrical Problem Tablet. So let's take a look at this. So this is a tablet. It's now in the British Museum. It originated, well, we don't know exactly when, but roughly between 3,500 and 4,000 years ago. And so a long time ago. And if you start looking at this tablet, the thing that's interesting is there's a lot of recognizable stuff here. There are diagrams. There are, we can see that's a square tipped on its side. It's got diagonals in it. We go down here, there's some drawings of what's on this tablet. And turns out this tablet is a collection of geometrical problems. They're ordered from the simplest to the most difficult. And presumably, this tablet was something that was used in the schools that existed at the time. In those days, sort of the big thing to learn was writing. And so there were these scribal schools that would teach people to write. And in those days, most people didn't know how to write. Widespread literacy is only 500 years old or so. In those days, it was a specialized group of people that were the scribes who knew how to write things and also knew how to do things like do math. It's sort of interesting to compare that with today, where computational language is the new writing, and it's still the case that only a small fraction of people know how to write computational language. No doubt the same will happen as happened in the transition from the scribal schools of ancient Babylon to the modern schools of today, where everybody learns to write and learns a certain amount of math. So this was presumably something which was something for learning geometry. Actually, we don't know, because all we have is this geometrical tablet. We don't know if this was viewed as an elementary school exercise or whether this was the kind of presentation of the finest research results of mathematics at the time. Although we do know that there were slightly more sophisticated things that existed at least a little bit after this. So let's take a look at some of the actual things that were on here. And we have, if you go to the website, you'll find there are interactive pieces here which you can play with, but then there's kind of a computational exploration of what's going on. And I think one of the things that's interesting, kind of you might ask, what was the most difficult problem on this tablet? The most difficult problem had to do with this figure here. Its name in some appalling, I mean, I think this is written in Akkadian, and I don't know Akkadian, and we don't know how Akkadian was said, but this object is an Absolumiku. This is a geometrical shape that doesn't get taught much in schools today, but was quite a popular thing in ancient Babylon, in the times of ancient Babylon, and Absolumiku. Absolumiku was also called a cow's nose, because at least in some first approximation, that's kind of the shape that you see on a cow's nose. And what you can see is that it's the shape that's made from that hole between four circles that are put together. And so the question for the kids of ancient Babylon was, on this geometrical tablet, was what's the area of that region here? So those who are kind of sophisticated in mathematics today might be able to figure this out. If you go to Wolfram language here, there's just, it's okay, this is the thing. There's a rectangle, there's a disk. You're basically asking what's the area of that thing, and out pops the answer 4 minus pi over 8. What did the Babylonians do with this? Well, the Babylonians, so pi, remember, is the ratio of the circumference to diameter of any circle, and its approximate value we know today is 3.1415926, etc. And probably people know more digits than I do of it. That value was progressively worked out over the course of years. In fact, one of our exhibits in this virtual gallery kind of traces some of the notable artifacts in the history of working out pi. But in Babylonian times, it wasn't known exactly what its value was. In the case of this particular tablet, the value that was used was 28 over 9. It's that which is 3.11111 recurring. So not too bad, close to 3.14, but that was the value that was used in giving the approximation to this 4 minus pi over 8 area that we now know is the area of the cow's nose figure. But it's interesting to see, this is what the Babylonian kids were doing, is working out things like that area. And it's kind of nice that I'm not sure at what grade level in modern education we would get to work that out, but that's kind of the sort of thing that was being done. There was a lot of, people liked a lot in those days, these kind of areas that were sort of these moon-shaped areas that were differences between different parts of circles and so on. And there are a lot of these problems that were set up that way. I think, let's see, is this the actual list of all the problems here? Let's see. The first problem, the easiest problem here, we have a unit square, extend a border 1/4 on each side, and then draw a second square. What is the area of that second square? So that was the first of the problems on this tablet, and we keep going to the more and more sophisticated ones here. Let's pick another one here. We have a unit square. Inside it, we draw 8 wedges. What are their areas? And we keep going, and eventually we're going to get to these things with circles. There's a question on the chat here about, did the Babylonians have a lot of curved architecture? That is a good question. Certainly the, let's see, the pattern that is made with these kind of loons, that does appear. I'm trying to remember, there is a very famous wall in Ur that is, according to legend, was made by Gilgamesh, famous for the Epic of Gilgamesh. Let's see if I can pull up a picture of that, and let's just see whether it has some, let me see here. I think I might have a picture conveniently. Yes, there we go. There's a good picture. Yes, this is from a book I wrote ages ago, not about history of, is about the future of science rather than its history. But this happens to have some illustrations of, so that is a wall that's the first example actually of mosaic from 3500 BC. And no curved stuff there, very, very digital. Could have been pixels, but people didn't really understand the idea of pixels for a lot longer. That's a piece of Phoenician design. That's something that, it's a design you see actually quite often in ancient designs. This design that it's kind of easy to make this because those are the kind of holes for a compass where you can draw a circle, and you're kind of drawing a bunch of intersecting circles there. And so that was a common motif. But I'm not aware of when I don't know much of that area has been excavated, so it might be known, but I'm not recalling that.
I've seen some paintings in the walls.
Yeah. Oh yeah, which have circular things in them.
Yeah,
I think some of the gates also had curved tops to them.
Yes, right. The whatever Ishtar gate.
Ishtar gate, exactly. Yep.
Has a okay. So, I think so anyway, so that's a first example of a place where we can kind of go back 4,000 years in history and identify math that we kind of know about today. Now, one question about that math, when we start saying, how do they write down the answer? Well, they have to write down numbers, and the numbers we have today aren't the numbers the Babylonians used. So a question we might ask is, how did people actually write down numbers? You know, we have our usual way of writing down numbers today with all the digits and, you know, the ones column, the tens column, all that kind of thing. One may know Roman numerals. Roman numerals worked a somewhat different way. How did Babylonian numerals work? Well, let's see if we've got a good example here. This is our gallery about counting. Let's see, I think this would show an example. So this is a multiplication tablet. I guess this contains multiplication table. So let's just remind ourselves what a multiplication table of today would be like. So let's go make ourselves a multiplication table. Let's just say, make a table of, let's say, A times B, A going up to, let's say, 12. That's what people usually go to these days. And B going up to 12. And let's say, let's just make a grid of those. Okay, now we have a multiplication table. That's what we mean by a multiplication table. So what did the Babylonians do to make their version of a multiplication table? They had to have a way of writing these numbers down. And what you'll see there is Babylonians, their writing and their numbers were all made using this cuneiform script. And the basic idea was this was a clay tablet. And when you had a little wooden stylus, and you would make little wedges in the clay tablet, and then you dry it in the sun, and then 4,000 years later, somebody would pick up the tablet, and it's still a nice hard thing, and it was a great way to record stuff. And that's one of the reasons we know as much as we do about Babylonian civilization, is because they wrote their records on clay tablets, which has survived for a long time. I have a little one here. This is this is not a mathematical one. It's just a receipt for I think it's a barley receipt. Let's see if that goes in focus there. Let's see if I can get that to focus. Oh, there we go. So that's a typical clay tablet from ancient Babylon. And the one that I'm showing here on the screen is a multiplication table clay tablet. And this is one where we can try and identify what was going on. How did these wedges mean numbers? Well, this is the scheme. The Babylonians had, and I'm not going to necessarily be able to tell you all of these numbers, but the simplest thing to do. Well, let's actually
scroll down one screen. If you scroll down one screen, it goes in sequential order.
Yep. Great. All right. Maybe I could actually compute these things, but let me just show you this as an example. So easiest way to represent 1, 2, 3, just 1 of something, 2 of something, 3 of something, 4 of something. Okay, arrange it in the pattern. You can kind of recognize it. 5 of something, 6 of something, 7, 8, 9. Okay, 10. Let's make that different. Now, instead of what we do in our number system, which is we just represent things positionally, we just say the last digit is going to be the ones column, the next digit over is going to be the tens column. In Babylonian, the Babylonian way of writing numbers, a little bit similar to the Roman way of writing numbers, the tens, a 10 was a different kind of thing, kind of like a Star Trek emblem kind of thing. And so that was 10, 11, etc. By the time you get to 20, you got 2 of those, and so on. And it builds up, making use of kind of these Star Trek things. I'm sure they have a more official name than that, and the sort of traditional wedges.
Chevron.
A chevron, right? That's yeah, chevron. Okay, and then let's see if we can pick this up here. Let me just here, let me just do this. When in doubt, use a computer to do. All right, we got a. Let's say we let's just check we can actually do this. There we go. So there's a Babylonian 10. Let's say, what is 100 like? Okay, that's what is that? That's got a new kind of object in it. And I think we'll start seeing the new kind of object at 60, because the Babylonians, now why are we seeing, oh, that's because, why is that a 60?
Because they didn't have positional representation. So if you see that, it could be 1, it could be 60, it could be 60 squared.
That's bad design. It's amazing their civilization
a while to figure it out
for thousands of years with that kind of goofiness. Okay, well, so there's 59, and we can see there's 5 10s and there's the 9, and okay, by 60 we're just it's just okay, it's just like a 1 again, huh? So 61 should show up as having oh, that's really confusing.
They would sometimes add a little bit of space between them. But if you can, so it's ambiguous positionally and it's ambiguous numerically.
Well, but they were very keen on 60, and their keenness on 60 has an echo today, because that's how come we have 60 minutes in an hour is from Babylonian times, and how come we have 360 degrees in a full circle, that's also from Babylonian times. And so the Babylonians were, that was kind of the base of their number system in some sense was 60, although the way their numbers work were a little different than ours. So let's see if we can actually make a, I guess we could just make our multiplication table here. Why don't we just do that? Why don't we make this multiplication table in Babylonian right here? And you can do that, by the way, on the website. You can do the same kind of thing. Let's do this here. So let's say we're going to make this an ancient Babylonian form, and let's see what this looks like. Maybe I shouldn't do such a big table at first, just because it may be hard to see what's going on. Let's just do a 4x4 multiplication table, and how about I put in A times B there, and now let's just work this out. Okay, there we go. Here, let's actually put grid lines in our grid so we can see it better, and you know, hopefully, okay, we might have gotten an A for this in an ancient Babylonian scribal school, although they didn't have A's at that time because the Phoenicians hadn't come in and invented the alphabet yet. Okay, so that's what a multiplication table would look like. Let's go ahead. Let's see whether we can actually make a bigger multiplication table here. Let's try and see whether we can do 10 by 10. And now if we've done this, okay, there's the multiplication table. Let's go look at that actual tablet from ancient Babylon, and let's see whether we can identify anything like that on it. Let's see up here. Can we actually find, is there some place where we can actually see on the tablet? Gosh, it's going to be hard to tell, isn't it?
Scroll down about 2/3 of the way down. There's a direct comparison against a version that you just made and the tablet.
There's a drawn piece of the tablet, and oh, I see. This isn't as simple a multiplication table. This is.
It's a 45.
It's a 45. Why did they pick 45? Somebody's exercise was 45. Maybe another kid got 44, but we don't have the 44 tablet left over anymore. Okay, but so the idea is, and this is why archaeology is hard, you know, going through and actually figuring out, yes, this little tablet really did have these things that we can now interpret in this way. When was the interpretation of this done? When did people in modern times learn how to decode all this stuff? It's like
early 1900s for these tablets. Might have been known earlier.
But the cuneiform script was known in the 1800s sometime.
pretty sure yes.
There. Okay, so anyway, I think on this tablet, the theory was I guess this was the kid who got the 45 problem to do. And it's kind of interesting to see how many years later is this? How old is this one? This is, okay,
Really
this
old.
is again about 4,000 years old. Let's go see what kind of grade this kid should have got on their homework from 4,000 years later. Okay, let's see. So the second line on the front of the tablet, how do we know that one side was done by a teacher? Is it different script?
The writing is stronger, more consistent. And I think there was also generally, there would be a couple columns, maybe not in this one, but the teacher would do it and the student would do it.
Okay, all right. So this teacher, that's a shame. So 4,000 years later, we discover that the teacher, instead of what should have been 90, they wrote that out. Shocker. Okay. And now what about the student? How did the student do? Did the student do, okay, 2 errors on that line there, writing out different kinds of things here. Oh, well, okay. So, all right, so we can see a little bit about how the Babylonians wrote out numbers here. Let's, maybe we should turn to something different. Actually, we could ask the question, if we look else at other times in history, how have people kind of done counting and arithmetic, and what are some different ways that you might do counting? This is, let's see, what is this? This is an earlier math tablet in which I guess there isn't yet as well developed. There's still those wedges. Is this using the same scheme for representing numbers or not?
No, this is earlier. This is the earliest known mathematical table that has been reliably dated.
And
so
how did they represent numbers?
As you see right there. But these are not just numbers. These actually represent either lengths or areas. So it's multiples of lengths or areas.
Ah, yeah, because they
didn't have the abstract number yet, I don't think, for this tablet.
I see, because that's the thing people had to realize, that a length and an area were the same. You could represent both of those just with a number, because you might have thought, you know, when people first started inventing weights and measures and areas of things, it's like, well, are you weighing, you know, barley, or are you weighing stone? You know, those might be different kinds of things. Can you represent those with the same number? And much worse, if you say, how long is it from here to there? How long is the ruler from there to there? That's a number. You can characterize that by a number. And then we count how many squares there were in this particular region, an area. That's also a number. Oh, you can think about those as the same kind of thing. And I guess back in the days when this tablet was being created, that unification of the notion of numbers can represent both lengths and areas hadn't happened yet. Well, if we go a little bit forward in history, let's look at some of these others. What's this one? Oh, this is decimal. Okay, so this is only 300 BC. So that was the time when in Roman numerals we have this kind of strange sort of mixed, not quite using base 10, base 50, base 100, etc. Scheme for doing things. The Greeks had a number system. I'm sure we've got. I wonder whether we can compute that here. Let's see. I wonder whether our ancient number representation system here.
I think you'll just have to use integer string.
Oh, okay.
Or related.
Okay, so let's see. If I say this and I say Greek, do I get something? Oh yeah, there we go. Actually, it's going to be easier if I say Greek lower, isn't it? All right, so this is, let's make that a little bigger. That is the ancient Greek number system, which let's see how this works. So let's just make a table of numbers here. Let's make a table of the first 20 numbers, for example. Okay, let's make that a little bigger. So if you know the Greek alphabet, you might recognize that the way the Greeks did numbers is they used letters of their alphabet: alpha, beta, gamma, delta. So alpha was 1, beta was 2, gamma was 3. So it's like if we were to say, let's just use in our alphabet, let's in modern times, instead of having a digit 1, let's use A for 1, B for 2, C for 3, and so on. That was the idea here. And one of the things, I've spent a lot of my time designing computational languages and so on. And so I always notice things which I view as design errors. If you know the Greek alphabet, you might know alpha, beta, gamma, delta, epsilon, zeta is the next letter. But in the number system, because they had sort of burnt in the order of letters in their numbers, they used to have another letter that was before that was used in earlier times. That's a digamma. So what is that? That's a 6. 6 is digamma. So they kind of goofed it. And it's as if we'd had an extra letter in our alphabet, which we'd put in our number system and then dropped out. So that was that's sort of an interesting little glitch in the way the Greek number system works. And we can keep going on, and we'll see things constructed using numbers. I think kappa is 20 there, and so on. It's worth commenting that, I mean, if we do the same thing with in Roman numerals, it's interesting to realize that the Greeks and the Romans used the letters in their alphabet to deal with numbers. And that was a time when I think that fact that they were using letters of the alphabet, things like words to represent numbers, was something that was actually very confusing when people tried to develop mathematics further. And for example, in developing algebra, where you want something to stand for any number, like X is supposed to stand for any number, that was really confusing to see when you were having things like X and XI being numbers. And actually it took the importing of the Hindu-Arabic number system around 1200 AD before people could realize that actually numbers and digits were a different kind of thing than things that you could represent with letters. And so I think the development of algebra, which happened eventually in the 1400s, was kind of slowed down by the fact that in the past people had kind of associated numbers with, they didn't really distinguish between arbitrary variables like X that could stand for any number and specific numbers. They were all represented with essentially letters like you would put into words. Okay, well, so here's an example of this. These are decimal. Okay, this is from China. And can you explain how this works? Well, let's see if we can look at the Chinese numerals here. Are they the same now as they were then? I don't know. Let's see if we
the forms have changed somewhat, and of course, there's now a simplified as well as a traditional, but more or less they're the same. Okay, so that's the 1, 2, 3 is kind of as we might expect it to be with 1, 2, 3 of something, and then it gets more complicated here. But so if we look at this bamboo strip from 300 BC, are we going to see the same? Are we going to see that it works pretty much exactly the same way? Yep. Cool. Okay. Except that they have special characters. Instead of just listing the digits in places, they have a character for 1,000, a character for 100, a character for 10 that is interleaved in there. I see. So they have a thing like the Greeks did, where they have a marker that says, well, I guess, I see a character to indicate which digit corresponds to which place. So 300, 2 10s, 1. I see. All right. Well, anyway, so let's see. Let's go forward here a little bit. Let's look at some other ways that people represented numbers. What's that? That's a place where oh, that's pretty hard to read. Those are Roman numerals, but somebody was writing with a wax stylus. These were thrown away. The surviving ones, they were not considered of any value, so they're all come from dump deposits. No effort was made to preserve them in libraries or such. Well, and they were just wax tablets, I guess. Were they used for? Was this for merchants calculating things? Or what? And students. Right. I mean, back in the day, it was the kind of the analog of quantitative finance of the day was being able to do fast calculations of, I don't know, interest rates, tax rates, things like this.
And so back in the well, even in the 1200s, people like Fibonacci, for example, famous for his rabbits problem and the Fibonacci sequence, Fibonacci series, you know, his big thing was kind of teaching people how to do arithmetic, because if you were a merchant who could do arithmetic better, you had a competitive advantage, so to speak. And in fact, Fibonacci was the person who brought Hindu-Arabic numerals to the West, and that was and advertised their value in, oh, you can calculate better with these things than you can in Roman numerals and so on. But I guess here this was a case where somebody was doing those calculations, I guess, in London. It said there this was found in London. Let's see. Well, this is an example of a different way of recording numbers. This is a Keepu from probably from Peru, and nobody really quite knows, I think, how these worked. These are presumably a way of recording numbers, but to this day, I think it's fair to say we don't really know how they worked. Is that true?
For decimal numbers, for storing numbers, they know how it worked. So it's a decimal.
Oh, really?
System.
Okay.
Yeah, you can see the demonstration there, and
Yep,
it's very simple actually.
Oh, I'm wrong. Okay, I thought this had not been decoded. Okay.
And usually they had an extra string to just have the recording of the sum of the values.
But a lot of what's on Keepus in terms of any other content, it's not known, but the numerical parts are understood.
That's right. Yeah.
So how did it work? So was it like you make? Is this a positional notation? Is this like our decimal numbers?
Yeah, exactly. And if you don't have any note, it's at 0. So they have this way of representing 0 for that particular.
That's
position.
cool. Yeah, the idea that there would be a number 0 was an idea that took a long time for people to grok. That was the notion of, well, we've got 1, 2, 3, that all makes sense to count like that. The notion of negative numbers or 0, it's like that was kind of a technological innovation that people argue a bit about when that came in. What's the, do we have some examples here of kind of the early,
negative signs.
Well, do we have negative signs? Do we have zeros? But that's a clever thing when you're representing numbers with knots. The unknotted string is very naturally 0. It's
as long as you space your knots out in a fairly standard form, and you know where it starts and begins, so you know where the 0 is. It looks like there's some special knotting thing at the end that tells you that's the 1's digit.
Oh, I see. There's an extra thing which says we're done now. But so how did they? I guess you can knot the string in you have to just figure out. You might start knotting it in the highest digit column, but that's kind of a funny thing. That's a left justified number. So if the numbers are a lot bigger, they hang down longer on the string.
Exactly.
That's it's interesting.
And if you're blind, you can still like keep adding numbers. Like for example, the Keepu were really specialized in doing that task. So
what was, sorry?
Like the ones who were like called Keepu that they were like counting and adding numbers. Usually they were old people, so they were blind and still like doing that task because it was very physical and 3D in the sense that they were touching the things.
Okay.
Yeah.
That's all right. I guess these are. When are these from? This is from the Inca civilization in Peru, and when are these from?
So they found like pre Keepus from another period of time, like older. Like it's probably 3,000 years old. The way of like recording numbers in this way, but for this case, it's from 1500. Yeah.
1600 it says here. Okay, so when the Spanish arrived, so to speak, they wrote down how this okay, this is a Keepu Kamayok, the chief.
That's what Bernat was just talking about. He's the chief treasurer and accountant in charge of all the Keepus.
Okay, so that's the secretary of the treasury.
Yep.
Of the or something, who was in charge of the Keepus. Interesting. Then, well, let's see. Actually, I noticed some comments from. We have a lot of different comments on different chat things, and I'm going to. There's a question from Guss here. Be interesting to learn what math was independently discovered in various cultures versus math that was discovered only once. Yeah, I think what we know, numbers were invented, different systems of writing down numbers, maybe 5 of them, is that right? I think sort of numbers were invented separately, multiple times. Most other math was probably not very independently invented. Arithmetic was kind of independently invented along with numbers, but by the time it gets to algebra and things, it was invented once. And it's a strange thing about math, and it's why by the 1600s, when our current mathematical notation, plus signs, equal signs, things like that, was getting standardized, that was done in a pretty conscious way as something that was just like Latin had been kind of the language of scholarship, the worldwide language of scholarship. There was an effort to sort of make math be kind of a worldwide language of doing math. And if you look even in modern times, you will find that the numbers differ in different places around the world, and you'll see in different countries, even in English, in countries like India, you know, there are terms, names for numbers, even kind of in English, that are different. But you find that by the time you get to the algebra level math, it sort of was the same all over the world. Now, in terms of geometry, that's an interesting question. I think that the idea of sort of doing things like proving theorems in geometry, that's something that was a very Babylonian and Greek concept. The idea that one would have a geometrical theorem, a result that says for all triangles and circles, this and that will happen. That was something Euclid, for example, in 300-ish BC, was the person who sort of systematized the writing down of this kind of formal proof kind of idea. And I don't think that originated in any other civilizations. I think that notion of kind of the philosophy of math, of doing proofs, was a Greek kind of idea that originated just in that one place. So I don't know of other examples. Do you guys know any other examples?
Of proof arising historically?
No. Of separate originations of mathematical ideas.
Yeah, I don't.
Well, I mean, certainly because of the lack of communication and large distances to travel, there were definitely things that are not taught necessarily in traditional Western math classes, but that were known in the East or were known in the Arab world. Right.
But in terms of the things that have survived to the present day as kind of notable pieces of math, I don't think there were lots of kind of, I don't think there were lots of lost mathematical civilizations.
I guess if we knew about it, it wouldn't be lost.
Well, it might have been found recently after we discovered lots of other things. Guss is asking, is there a Rosetta Stone for ancient math systems where multiple systems are presented side by side? I do not believe so. I don't think I've ever seen any artifacts where multiple different, for example, numeration systems are shown. Have you guys seen that?
No.
Yeah. All right, well, let's go look at a few other things here. Maybe we can look at, we started talking about, actually, let me just finish on arithmetic and then let's go talk about a little bit about geometry. Well, let's see, what else do we have on arithmetic here? Well, I think we've got some talking of math education. Let's see. These are, this was a strange tradition in education, these things called horn books. This was the kind of, I don't know what it was. It was kind of like the this was the student remembering this kind of strange paddle-shaped little thing that you could like hang on your belt or something. That was a way of remembering things like the letters of the alphabet or the Lord's Prayer or math. And this is one, I guess, it's hard to date these things. This is a US, North American one, a horn book. I guess it was called a horn book because there was a thin layer of horn on top of the paper, presumably as a protective, as a way of, you can carry this around everywhere and it'll be safe type thing. But this was a sort of a way to, this was kind of the way to remember things circa 1600s or so. Let's see, we have here, what do we have here? This is, oh yeah, this is a good one. So back in the day, when people would learn math in, well, certainly in America, and I think also in places like Britain and so on, the common practice was to write these so-called ciphering books, which were ciphering these days usually has to do with codes and cryptography and things like that. Back in those days, it had a different meaning. It was a book that you would write out that contained examples of mathematical calculations that you would do and different kind of math problems you would solve. And you would write this book out. And of course, there weren't, people didn't tend to have printed textbooks in those days. So you would write out your ciphering book over the course of years as part of your school education. And then you keep your ciphering book. And whenever you wanted to work out that calculation for, I don't know, something to do with your land or whatever else, you would, or whatever else you were working out, you would get out your ciphering book and go look and see what was the, how did I do that back when I was 10 years old or something, and that will be the reminder. So some famous ciphering books have survived. This is Abraham Lincoln's ciphering book, and you see his efforts to learn, I guess was this long division?
Yep.
Did he get it right?
Mostly. And then there's a check there, that casting out nines with a big X and numbers all around it is a check.
Yes. Yes, well, maybe you can explain how that works. One of the things that's funny about math education is that people, when they say, oh, here's how you do long multiplication, long division, things like that, at any given time in history, there's always a popular method for doing this, and it's changed over time. So when you look back at old books, there are these, the rule of Z's was a big thing. I think that was, do we have an example of that? That was Richard Record, who was the first guy who wrote a book in English about how to do arithmetic. He had this magic scheme called the rule of Z's, which was a way of doing calculations, which is completely lost today. There are lots of different ways to do it. Now, what does casting out nines do?
It's basically using the digital root. So it's using the fact that the remainder, you add the digits and keep doing it until you get something.
So wait a minute, what's it for doing? It's like a check digit.
It is a check.
Did I get the right answer?
Yes.
And so what you're doing is you're taking the original thing, what the things that you're multiplying or something, or the things you're dividing?
the divisor and the A and the B in the division problem, and you're basically finding the digital root for the product of those, each one individually. And
what is the digital root?
Oh, that's where you add the digits until you get a number, and then repeat the process until you get it down to a single digit. So it's basically the number mod 9.
So wait a minute, if you take the number 123, you mean you just say 1 plus 2 plus 3?
Yes.
That's called the digital root?
I believe so.
Wow, they teach different things in math. I never heard of that. Okay, so anyway, there's a math theorem, I guess, that tells you that if you take that quantity, then it must have certain properties when you do division of two numbers. Is that right?
Yeah, basically, because of the way it works, the digital root remains unchanged or has a specific pattern when you do multiplication or division. So you can check that it has to have a certain, like the 5 and the 5, I think those have to be the same on top and bottom. and they come from different parts of the
But wait a minute,
computation.
so this is the thing kids could do today, right?
Yes, absolutely.
Do kids do this today?
They use calculators and computers today.
Oh, okay. But if they were if they were really faced with the problem of doing this calculation, they could check their work by doing this trick, just like Abraham Lincoln did.
I had heard of it, but I had never actually used it until encountering the fact that Lincoln had both heard of it and used it. You can see Abraham Lincoln's book is written in very pretty, yes, calligraphy down at the
people
bottom.
wrote much better in those days. So let's see, what else did Abe write here? What are the kinds of things that he have? A compound division. Now, Abraham Lincoln was quite a math enthusiast, I think. It's said that he would take a copy of Euclid's Elements, Euclid's book of geometry results. Actually, the Euclid's Elements is the second most widely printed book in history after the Bible, and it's a book of geometrical results. But it's Abraham Lincoln is said to have taken that book on the campaign trail with him as a way to if he wanted to sharpen his mind, he would do a geometry proof or two. Let's see, what is this?
You can see some of the. There's a one on simple interest. He has them very neatly labeled.
But this is the single rule of three. So that's another thing that's been lost in math education: the rule of threes, the rule of sixes, and so on. The rule of threes is some kind of thing about multiplication and division of numbers.
I think it all relies on modular arithmetic.
I think this is a little bit of a different thing. This is how to remember when you're doing X% of Y and so on versus that of Z.
Oh, yes, I think you're right.
The double rule of threes. Okay. Well, these are things that have been lost. Okay, the double rule of three application, spelled wrong, maybe. Well, spelled differently than we spell it today. You never know if it was, spelling didn't get, well, it was standardized by then. Okay, there's simple interest. There we go. Well, so.
He's probably a better mathematician than most modern politicians. I think it's fair to say.
Who's to know? Except in France, where I think that seems to have, at least historically, been an exception. Let's see, what's this? This is Orville Wright's arithmetic textbook. Okay, so if you're going to learn to build a flying machine, you better first learn arithmetic. So that's, did he have many notations in here? This was the American Intellectual Arithmetic, an extensive collection of practical questions on the general principle of arithmetic. Okay, a good thing to know if you're going to build a flying machine.
It was a very widely used and popular textbook, and I think this particular one is of main interest just because it belonged to the co-discoverer of flying, and he drew some interesting doodles and other things on it.
So let's see, by 1907, this is an arithmetic exam for this high school exam for the University of the State of New York State Regents exams. Don't they still have New York State Regents exams? That can't have changed in 100 years. But do they still have the same kinds of questions on them? Let's see what
the questions are quite impressive. I think high school students would find many of these extremely challenging, and not to mention college students.
The total assessed valuation of a certain city was $65,489,000. That's kind of small by today's standards for your average city, probably. The total amount to be raised by tax was $229,000. Find the amount of tax to be paid on a piece of property valued at $12,000. Okay, that's probably a thing you could solve with the rule of threes if I know what the rule of threes was. Given inches, the length of the meter, that's interesting. 1907, people talking about metric. I guess the longitude of Cincinnati is 84 degrees, 26 minutes west, and that of Berlin is whatever. What is the difference in time? Wowee, that's pretty hard. So you have to, yeah, that's a serious calculation of I mean, you have to convert the hours, minutes, seconds of Oh, actually, it's not as hard as I thought.
Yeah,
Oh, I
just
think I still
subtract
gotta
and divide by 15, the number of degrees roughly.
Okay, okay. Okay, find the square root of 170,569. Okay, who knows how to find square roots by hand? You know, when I was a kid, calculators came in when I was about 12 years old. And so I just missed learning how to take square roots by hand. But I guess back in 1907, people did that. Well, let's have a quick look at a few other things in our exhibits here. There's some good things on the Pythagorean theorem, some interesting things on prime numbers. But let's have a look. Let's look at pi just for a moment, and then we'll take a little look at polyhedra. So pi, okay, conveniently a circular tablet that has an approximation to pi written by the Babylonians. That's okay. So this was pi being approximated as 3, which is okay, not as impressive as it could be. Let's see how pi gets more impressive. Okay, this is approximating pi. So instead of working out the ratio of the circumference to diameter of a circle, how about you approximate the circle by a hexagon with just 6 sides, and then that gives you an approximation to pi. And I guess that was a later Babylonian effort. What's this? Is this okay? So this is using more and more sided polygons to approximate what the value of pi would be, because if you have enough sides on the polygon, eventually you'll have something that's like the continuous arc of a circle. But this is, so how big do they, this is 300 AD. This is, how far did they get?
They got pretty far.
How many digits did they get to? Oh.
Okay, I think at least 5 or 6.
Okay. By 12-sided polygon, they could calculate the area, because what they did was they knew how to work out the areas of triangles. So they could figure out how this, and they could figure out, how the angles of triangles related to the lengths of their bases and so on.
And he actually extrapolated, Stephen. So he got 3.1416, got a rational number approximating it to 5 digits.
And they did that, but they did that by just working out, how many sided was that polygon to achieve that?
I think he went up to 10 sides and then extrapolated.
Oh, I see. So he did the 5 sides, 6 sides, 7 sides, and then he looked at how that series was converging. Boy, that's a lovely piece of it. Come on, we should be able to do that. How does that work out? I mean, if we work out, let's just say polygon, regular polygon, we got to be able to do the same thing somebody did in 1700 years ago or something. Let's see. So if we do regular polygon 6 or something, and we say, let's say perimeter of that, right? Are we going to get, that's a perimeter. Oh, that's perimeter 6, which is kind of obvious. But now, how do we work this out? We're working out. That's because it has. So what we want to know is what if we worked out the area of this, right? We would say, if we work out, that's a little bit of a cheat way to do it, but if we could do this divided by the area of the regular polygon. So what's the area of a regular hexagon? Let's find that out. If we say the area of a regular polygon, 6, okay, 3 times square root of 3 over 2, which they won't have known in terms of square roots, but they will have perhaps been able to find a numerical approximation to that. So let's see what happens if we say regular polygon of n here, and then we say n here. Let's see whether we can get that to converge to something. So let's make a table of those. You said he went up to 10. So let's see, the smallest number of sides is 3. So 3 to 10, okay. So let's work out what those numbers are. Now, what am I seeing here? This is, why am I not getting the right answer here? These are polygons whose sides, you
have a unit polygon.
A unit polygon in the sense that its sides are of unit length, rather than its diagonals of unit length.
Yeah, that.
Okay, how do I fix that? I mean, I should be able to use the fact that the area of a circle is pi r squared, So the area of a unit disk is pi r squared. So here, each one of these, I could say, let's see, what do I want to do here? I want to say the perimeter, come now, we should be able to work this out.
You can specify the radius in regular polygon. You can say
Yes.
r and then the n.
Yeah,
So
that's the way to do it.
You can put a 1 there.
Oh, okay.
At the beginning.
Okay. Well, that's
like the other
first
way,
argument. First
yeah.
argument.
Yeah,
Oh, okay.
precisely.
I say
I
the
think.
regular, the 1 and then n, like that.
Yeah.
Okay, let's try this.
2 pi.
Oh, look at that. That's a very good, that's a pretty good 2 pi. Because that's divided, that's the 1 was a radius, so it's 2 pi r would be the formula. Okay, so there we go. Now we're cooking along. Okay, so let's
and
take
if
a
you
look
plot
at
that, yep, exactly.
So let's do a okay. So that was what that person back in 300 AD was seeing, was that series of numbers, and he kind of took that curve, I suppose, although I bet he didn't plot it.
If you do it on a log plot, it's nice and linear.
Well, it's so, but this is approaching.
Yeah.
This is approaching some number. So if we keep going, let's do this a lot further. Let's do this. We're going to get all kinds of wild things if we do this. If we do this exactly, let's do to 100, for example. Oh, well, we didn't get too much there. Okay, so now let's do a.
Well, you just found the closed form. Yeah.
Oh, look at that. Okay, so that is going very close by the top here. But let's look at this on line 30. Okay, we're getting 3.141. By the time you've got a 100-sided polygon, the estimate for pi will be pretty close to that. If we work out, let's find out what it is. If we say pi minus all these things, we'll get the size of the difference. So we're now getting 0.0005 for a 100-sided polygon. And if we do what Eric was suggesting there, and I make a log plot of this, then it's not quite linear. This is showing kind of how this is like in powers of 10.
Yeah, you're going in you're going, linear n. In the case they were actually considering, they were bisecting each time, so they were going 2 to the n. So in the log plot it became linear. Yeah.
So it becomes easier to see what's going on then. Okay, so anyway, so that was the next effort of pi. And they managed to get what, 4 digits by 300 AD in this?
4 after the decimal, or 5 if you count the 3.
Okay, so this was the really sophisticated thing. 1610, Ludolf van Coulen, and that's why in continental Europe, pi was sometimes called Ludolf's constant, because this particular individual managed to compute pi really pretty accurately, and so he had that on his tombstone. He had, look at all those digits. That was pretty impressive for 1600. How long did it take him?
I believe most of his adult life.
Oh, it says here, most of his life, right?
Yes.
Was spent computing those digits. How many did he get?
How many is it? I forgot now, but I'm sure I wrote it at the time. Let's see.
Okay, well, when it goes up to 36 here, so I'm going to guess he got 36 digits. Well, so then let's see how. Okay, another question is, how did pi end up being called pi? Actually, it was a chap named Jones, British, maybe Welsh chap, and this was the first place where the name pi appears. It was kind of, pi was kind of the Greek letter that stands for P, and P kind of stood for perimeter, and it was kind of like, that's the perimeter of a circle is a P. Pi got kind of famous through Leonhard Euler, who was a very prolific mathematician of the 1700s, who invented many things, also popularized the exponential constant E, which isn't Euler's constant, that's a different thing. But Euler popularized that, and he also popularized pi, and that's what really cemented the name. And pi has had many adventures. This is a famous one, which isn't, I think, the story isn't quite as it's sometimes told. But there was a time when an effort to legislate the value of pi, which doesn't make a lot of sense because pi is something you compute mathematically. It's not something where you just decide it's this value. Although that's a confusing thing because some things like the meter, for example, is one just decides what its value is. It's a thing that is, it's something where it's just a matter of, in terms of the second, the meter is determined by it's something where we decide what it is. It's not a thing that comes from nature. It's a thing that we invent. But pi is a thing that sort of comes out of mathematics. It's not something we get to invent, or we get to say, we're going to decide that pi is going to have such and such a value. And obviously, if we did decide that pi had such and such a value, things would get very, very confused, because when we work out something that uses mathematical facts about pi, when we work out the next thing, it will be inconsistent because we didn't get the right value for pi. All right, let's just look at a couple more things, and then we should probably wrap up here. We can take a little look. Should we look at polyhedra just for a moment? Polyhedra are wonderful because they're things where, you find an ancient icosahedron, and you have a modern icosahedron, and by golly, that ancient icosahedron looks really modern, because the icosahedron is the icosahedron and has been that way forever. It's something that is just a mathematical structure. And that's kind of one of the great things about mathematics, is that it has this kind of permanence of the ancient Egyptian die that is in the shape of an icosahedron is still the same icosahedron shape that we have today. People don't use icosahedral dice that much in modern times, except for things like Dungeons and Dragons and so on. I guess they were more popular back in those days. What did this die that has Greek letters on its faces, and what could you? So there's the Greek numbers I was showing earlier. So there's delta, gamma. That's iota, delta. So that must be a delta is a 4, a gamma is a 3, an I delta is a 14, and so on. And there's the digamma showing up, but that must be a 16 there. Does one know what this dice was used for in
gambling, most likely?
Gambling, and also divination. There are some temples recorded in Greece that they were like having these dice and a tablet with all the results for
right. So it's kind of like, I want to know what's going to happen tomorrow. Let me throw a dice and I'll make a prediction about it. That's that's a much more civilized way to do it than the horrible things that involved various kinds of animals and so on. Much easier to throw a dice. Fair enough. Well, so that's oh wow, these are. Oh, I see. This is icosahedral dice from from Roman times, where this is like throwing horoscopes or something, because these are names of gods and so on that are listed on the faces. Is that right?
Exactly. Mm-hmm. Yeah.
What was the kind of idea here? So you would throw one of these things, and what do these words mean? I don't know that this is.
So if you scroll down, you're gonna see so that they had these attributes associated.
Those are the different gods, and those are the attributes that the god you rolled has.
Oh, I see. So in other words, if you rolled that god, it's like good time to go.
Yes.
Home. Good time to weave tomorrow.
To go to war.
Okay. Was there a what kinds of things could you end up doing? Oh, I see. These are the gods, and of course now in our modern computational language, we have a computational encoding for Isis, and no doubt has all sorts of attributes.
Correct.
Okay, Thoth was the one to get here. If you wanted scribes, writing, wisdom, mediation. Okay, if you want to build a pyramid, get Ptah. So okay, let's see, what else do we have here? Maybe we can end with this. This is a kind of a fine thing. This is from somewhat later, 1596. Johannes Kepler was a fine mathematician who sort of discovered some pre-calculus kinds of things, but he didn't have things like mathematical notation. So when he wrote his great works about astronomy, he was using musical notation to indicate, because musical notation had been invented in 1000 AD. So the kind of standard putting of notes on a stave and so on, that had been invented much earlier. But he kind of used, that's why when one talks about the music of the spheres, to do with sort of early astronomy, that was because the notation that Kepler was using was actually musical notation to represent, so the planets, Kepler was very concerned with the planets that had been something of interest from Babylonian times. In Babylonian times, people had been interested in, can you predict where the planets will be at a certain time? It's a notable feature that the Babylonians, for 800 years, they recorded every single day. They made a kind of a diary of what was going on in the world. And they recorded the positions of planets. They recorded the weather. They recorded the height of the river. They sometimes recorded grain prices. And occasionally they would write such and such a king died, or such and such a battle was won or lost. But mostly for 800 years, they recorded every single day the kind of what had happened in the world at that time. And in particular, they recorded the positions of the planets. They're very interested in the positions of the planets. Actually, a couple of percent of those astronomical tablets recorded for 800 years have survived. Actually, my son Christopher has been doing an effort to make a computable version of those tablets now, so that you can go and see what the Babylonians concluded about things. Kind of fun, because it's the longest running kind of scientific experiment for 800 years. But anyway, so back in Babylonian times, it's like there are planets, there's the weather, there's battles. And one of the things that's sort of interesting about divination is people were wondering, what can you predict? Can you predict where the planets are going to be? Can you predict what the weather will be? Can you predict who will win or lose a battle? And to the Babylonians, the efforts to do those things seemed like they were about equally difficult. Today, we know it's a lot easier to predict where the planets are going to be than even whether it's going to rain tomorrow, and much more than who's going to win or lose a battle. So, but the Babylonians actually did succeed in making some predictions about when planets would show up in different places. And they did that by looking at these observations and by essentially interpolating, by more or less estimating from sort of this had happened now, then we know there's sort of a trend and that's going to happen later. But people were very interested in how to systematically think about kind of where planets were going to be and so on. And also to understand why were the planets arranged the way they were. It was known from Mercury out to Saturn, the planets were known. And the question was, why did our heavens, so to speak, have those particular planets with those particular periods of motion and so on, times they took to go around the sun and things like that, and not other ones? And Kepler had a theory. Kepler's theory was that the planets were kind of arranged on these kind of concentric spheres. By the way, this idea that the planets were kind of rolling on spheres of some kind or another, this was an idea that existed in ancient times. Particularly Ptolemy had that idea and made up these kind of epicycles, which were kind of this way of thinking about the planets as kind of rolling on kind of gear-like assemblies of things. And Ptolemy had a way of working out where the planets would be based on this collection of epicycles. It's kind of an ironic thing that in modern times, when we do precision calculations of where planets are going to be or where the moon is going to be, the moon is particularly difficult to work out the position of for working out things like eclipses, whereas Ptolemy talked about, maybe 3 or 4 epicycles, like 3 or 4 gears. We might now, we actually use in our calculational methods, even though that's not the physics of how it works, in our calculational methods, we still use the same kinds of methods that Ptolemy used, except now we have 100,000 gears rather than 3 or 4. But Kepler was very interested in why were the planets arranged the way they're arranged. And he had a theory. His theory was the planets are arranged the way they're arranged with these kind of epicycle-like different planetary, different sizes of orbits and periods of planets and so on. They were arranged that way because if you take polyhedra, if you take, so there are 5 regular polyhedra, the so-called Platonic solids named after Plato in ancient Greece, the tetrahedron, the cube, the octahedron, the dodecahedron, the icosahedron. There are 5 Platonic solids. Those are the only solids that have the feature that every face is the same around the solid. Those are the only ones you can make in 3 dimensions. In 4 dimensions, you can make some different ones and so on. In 2 dimensions, obviously, you can make an infinite number of different regular polygons with different numbers of sides. But in 3 dimensions, there are more constraints, and you can only make 5 of these regular solids, the Platonic solids. So Kepler's idea was, let's organize, we can see why the planets have these radii because it's something to do with the Platonic solids. He didn't, I think, imagine that there were giant, archaeoastronomy, made by giant struts made in the solar system. I think he imagined it was some kind of more theoretical kind of way in which the polyhedra would occur. But anyway, what he discovered is if you arrange the polyhedra in a certain order and you say around each polyhedron there should be a sphere, and then you make the next polyhedron out be the smallest it can be while still keeping out of that sphere. So you successively nest the polyhedron sphere, and you keep going, and you put the polyhedra in a particular order, you get something which was a pretty good approximation to the planets, to the orbits of planets at the time as they were known at the time when Kepler was writing this. So this is kind of the idea. There's an in circle, that's the biggest circle you draw inside the triangle. There's a circumcircle, which is the smallest circle you can draw outside the triangle. And you're doing the same kinds of things with polyhedra. So that's if you were doing it with polygons, but now we want to do it with polyhedra. And someplace here, we're probably going to see that happen with polyhedra. Let's see, it's a bit of a more complicated calculation. And someplace here, we're going to figure it out. Okay, we've got, we're beginning to construct here this is impressive that Kepler managed to do this without no Mathematica, no computers. Kepler managed to figure all this stuff out. Kepler kind of had a business actually figuring out kind of geometrical things for people. He had, let's see. All right, we keep going. And in the end, there's a particular arrangement of Platonic solids. I don't know quite what the order is, which agrees with the observed radii of the planetary orbits. And so one question is, there's Kepler's arrangement. The question is, did he do the best he could? Or is there actually another arrangement of those solids which would have given him, this is our, that's our version computed purely synthetically. Is that our version? And that's his version, yeah?
Left is ours, right is original. Yeah.
Okay, fine. I'm just checking. Yeah, okay, that's ours with all the image processing effects and everything to produce something which is as if it was a woodcut from 1600. Okay, so the question is, how well did Kepler do? Okay, this is Kepler's approximation based on these solids, but he didn't do too badly. Kepler's estimate and the actual distances, but how could he have done? Could he have done better?
Did he ignored metaphysics, which was probably almost as important to him as the mathematics. So he was a good mathematician, but also a very strong metaphysicist.
I thought I was just inventing. Somehow metaphysics is this thing that seems to come out of our recent discoveries about fundamental physics. So metaphysics back in the days of Aristotle was meant something a little different. So he had an argument for why the order would be this particular order. Is that right?
Yes.
Yeah.
Wow.
And then
believe that the Earth should separate solids that can float, as opposed to those that stand upright. Wow. Okay.
So, yeah. So the inner planets have the pointed vertices of the platonic solids, and the other ones are more. They have the one face flat. That's what he was.
Oh, okay. So it was when you got further out, you had to be able to put the things. It was you put them flat on something. So okay. So how did if he hadn't done that metaphysics, would he have been able to get a better result?
So he got the best result possible with his metaphysics. That's the top one is his.
But now, if you don't do that, if you don't say the pointy ones, the inner planets have to
then scroll down, and I think he got number 7.
Okay. So if you ignore metaphysics, you get better physics.
Yep.
Or at least a better explanation of our particular solar system. And of course, what we now believe is that the solar system formed by just an accretion disk around the sun, and the details of the particular orbits of planets are sort of coincidental, because maybe our solar system even had lots more planets at one time in the past, and some of them got lost by being ejected from the solar system or colliding with each other. So there isn't the kind of great significance to the distances of planets that people like Kepler or the Babylonians thought that there was. But it's interesting to see these kind of mathematical things, and it's kind of it's fun to realize that we can take what Kepler did here, and it's interesting to get some sense of how difficult the mathematics that was involved in what Kepler did was, and see sort of how difficult is that for us to do today. Well, okay, I should wrap up here. We went a little bit longer than expected. I'm happy if people have questions. I'm happy to try and take them. I would like to encourage people to look at the website. It's now open for everything, and to go and look at the interactive components here, and to actually, you can go ahead and open up something in the cloud and just start doing your own computations and see whether you can do better than some Babylonian student did, or whatever else. There's also going to be another session about history of math done by Eric and Bernat here, to going through more of what's gone on this website. I mean, to me, the thing that's sort of interesting is mathematics is a very conceptual area, and it's interesting to realize that there are actually artifacts that record some of the history. Some of the history is just what people knew and how people learnt things, but some of it is concretely realizable. And I'd kind of imagined when we first started thinking about this history of math effort that some aspects of this would be kind of sort of an adventure story of tracking down these kinds of different mathematical artifacts. And it has been something of an adventure story. And maybe Bernat and Eric next time will tell some of the adventures that have happened in the effort to find things, because there hasn't been a National Museum of Mathematics before MoMath. There hasn't really been an obvious reason or place to say, let's go find the artifacts from the history of mathematics. Now there is, and I think the exciting thing here is that we've sort of identified some of the kinds of artifacts that exist, that record the history of this sort of great enterprise that our civilization has done in building up mathematics. And the challenge now is to see whether we can actually set things up so that sometime in the future, right in Manhattan, some of these artifacts will be collected, and we'll actually have a place where one can see the original things that were the building blocks in some quite literal sense for what is now our modern ideas of mathematics, and can kind of see back into history those things where you can identify from the typical school exercises we see today. It's like, well, that was done hundreds of years ago or thousands of years ago, to things where you look back at what was done historically and you say, if only they'd figured out the idea of zero or something like that, things would have been so much easier for them. And it's kind of, I find it interesting to realize, what were those things which had this feature? If only they'd figured it out, then things would have been so much easier. Because when we think about things today, we're very keen to know if only we could figure it out, then things will be so much easier. And it's good to kind of get some intuition and some practice about what those sort of discoveries of the past were. So let's see, we have a few questions here. There's one from Fred, which I think is, what's the biggest number I've ever counted up to? You know, I think I remember when I was a kid thinking about that question of how big a number could I count up to? Could I count up to 1,000,000? You know, a really good thing to know is that there are about pi times 10 to the 7 seconds in a year, about 3 times 10 to the 7, 30 million seconds in a year. That gives you kind of a sense of how long it's going to take to count to different kinds of numbers. Of course, the way of counting up in numbers is if you count the 1, 2, 3, 4, 5, et cetera, and you name every number, that's a really inefficient way to count numbers. Back in the day, one might ask, how high numbers did people count in antiquity? How high did people manage to get, you know, did Greek mathematicians manage to get in counting numbers? The winner, I think, so far as we know today, is definitely Archimedes, a distinguished mathematician of, what was it, around 150 BC, I think, lived in Syracuse in Sicily, and was responsible for many things. But Archimedes had this problem of the sun cattle, and it was a problem where the solution to that problem is a very big number. But Archimedes actually had an article. It was a very early kind of scientific paper-like article. It was the thing called the Sand Reckoner, and Archimedes wanted to work out how many grains of sand were there in the universe. And that was very impressive that he could try to do that, and very impressive that he could sort of, you know, conceptualize those big numbers. I think he worked out, he tried to work out how big is the universe. What was his estimate for the size of the universe? I believe his estimate for the size of the universe is that it was about twice the distance from the Earth to the sun, kind of, which he kind of knew roughly what that was. And that was it was like how many grains of sand would fit in that volume. And he had some pretty clever ways to write down very big numbers. In today's world, we usually think about writing down numbers, you know, 10 to the power whatever, which means a 1 with some number of zeros after it. And so, you know, a famous number is a Google. The Google company's name was a misspelling of that name. A Google is Googol, and that was kind of made up by actually a kid in New York City, I think, long ago, as the name for the number 1 with 100 zeros after it. So that's a fairly big number. But if you say, what about 1 with that number of zeros after it, you get to a much bigger number. In our universe, well, there are only about a 1 with 80 zeros after it. That's the total number of atoms in our universe. So it's a fairly modest number. In our current theory of physics, the number of atoms of space, the number of independent points that exist in space might be around 1 with 400 zeros, 10 to the 400. And the number of different possible threads of existence in our universe is a much bigger number, maybe 10 to the 10 to the 300. Those are big numbers from today. But yeah, no, that's so. I myself can only claim very modest counting of numbers. Okay. There's a question here from Parmenides. Would we ever think of translating some of the books that haven't been translated into English, like Pascal, Emmy Noether, Riemann? I don't know how many of those have not been translated. You know, I'm always a big believer in reading the original version of things. It's sometimes with math, the notation of the original people who invented things is a little bit hard to understand because we've managed to develop our notation in a very clean way, like you know, things like, well, the notation of today, like equal signs and greater than signs, that was all invented in the late 1600s. And for example, people like Leibniz, he had a very clever scheme instead of a greater than sign, this number is greater than that, he showed it was kind of like there were two scales, and one of the scales was having something heavier than the other one. And so that was kind of his scheme for, that was the way of representing what was the bigger number. Now, it's a little hard to read that stuff today because we're used to just seeing the greater than sign, but it was kind of a clever idea. But so it's sometimes hard to read through those early notations. It's always interesting to see kind of how things were presented when they were first presented, because often the presentation is actually very clear. Sometimes the presentation was addressing kind of things where people said, I wonder how this works. And that wasn't, and that particular issue is not one that we care about today. For example, when matrices were invented, matrices today, it's just kind of, we think of them as arrays of numbers, and it's pretty easy to understand what they were. But when they were first invented, they were invented by Arthur Cayley in the late 1800s as part of the theory of invariance, and it was a whole elaborate story. It was related to group theory and all kinds of things about determinants and so on. It was a big kind of complicated mess of mathematical ideas, rather than just saying it's an array of numbers, which is what we say today. So in that case, looking at the original work is actually pretty confusing relative to what we have today. I think it's ironic that, for example, set theory, we just got a set of objects and we talk about the union of those objects or the intersection objects that are common to two sets, those kinds of things. That was invented by Georg Cantor, also in the late 1800s. And his original reasons to invent it had to do with some very obscure mathematical, well, today, obscure things about if you add up trigonometric series, you have sines and cosines, and you have an infinite number of sines and cosines that you're adding up. Will you get a series that converges or not? And when will it converge and when will it not converge? And it's a really elaborate story. And that story ends up being the question of when it converges and when it doesn't. He was sort of describing where does it converge, where does it not converge. That turned into set theory. But set theory is something, at least when I was a kid, there was the then new math, where one of the ideas was just teach set theory, it's easy. Well, it hadn't been easy for Cantor because he came to it in this very, very, very complicated way that also related to transfinite numbers and all kinds of elaborate things. It just turns out that you can pull out of that this fairly straightforward idea of just taking objects and sets of objects and seeing unions and intersections and so on. But yeah, it'd be interesting. I didn't know that those works were not translated into English. That would be an interesting thing to see. I think particularly, I would guess that of the three you mentioned, Pascal, Emmy-Noether, and Riemann, I would guess that Pascal might be a little bit more difficult to read from the 1600s, because I think that a lot of the ideas that we have today won't have been as clearly enunciated by the time of Emmy-Noether and Riemann, particularly. Bernard Riemann was I know more about him than Emmy-Noether was also had some nice, clear mathematics, so to speak. All right, well, let's see. I think there were other comments here, and I don't know what I should be looking at here. Gosh, lots and lots of comments here, but I think that's maybe we can, if there are other things which count as questions, I can try and address them all. William is asking, what counts as counting? What does it mean to count numbers? Yeah, that's a curious thing. What does it when you have if I say I've got my computer and my computer is I think you have to say, do you express the number in some way, like giving it a name, as Archimedes did? All right, well, it looks like we're out of questions here. And there's comments. I see all these comments. I should have been looking at these comments. The crows can count to 4 and so on. Yeah, it's always a curious thing. What kinds of we don't know much about how to interpret things that we don't know if the whales have a great system of describing numbers We just haven't decoded that, and it's hard to know. Oh my, these are getting more difficult. I think it's probably time to Gauss, somebody whose handle is Gauss, sent in the question, who do you think was the smartest mathematician in history? It's kind of funny that, you know, if you look at mathematics as we have it today, and you look at kind of the origins of the ideas in mathematics, there are certainly people who've contributed very big swaths of ideas that have been important surviving ideas for today's mathematics. I mean, certainly from antiquity, Euclid is surely the winner in terms of the sort of direct communication, direct sort of transfer of mathematical knowledge from antiquity to the present day. Euclid himself, well, essentially nothing is known about Euclid. Euclid is thought to have lived in Alexandria in Egypt, which was the site of the great sort of library of the ancient world, and Euclid worked at the library. The library was really a university of its time, and Euclid was is believed to have been kind of a teacher at the university, a professor in modern terms. But essentially nothing is known about Euclid as a person. There's a famous story, but it's probably quite apocryphal, of somebody asking, you know, what is the value of learning this mathematics, this geometrical mathematics? And Euclid was like, you know, gave some coin as I forget, actually now I'm forgetting the story, but basically the point was there is no sort of sort of pragmatic gain. It is an intellectual kind of exercise. Of course, there was plenty of mathematics that was more in the time of ancient Babylon and Greek times and so on. There really, and for a long time, there were really two branches of mathematics: arithmetic, things with counting and numbers, and geometry, things with geometrical figures. And those originated in accounting, with and that turned into arithmetic, and land surveying, figuring out, you know, how big was this plot of land. That turned into geometry, and those were the sort of two big branches of mathematics. And they, you know, arithmetic kind of turned into algebra when by the 1400s and so on. But in any case, I think Euclid. We know very little about Euclid. Most likely what Euclid was doing was mostly making a clear presentation of results which had actually been known for a long time, probably particularly known in Babylon. We know, for example, Pythagoras' theorem. I mean, Pythagoras was a colorful character who lived, eventually lived in southern Italy because he was ejected from other places. Pythagoras ran a cult that had all kinds of strange beliefs, so kind of interesting, strange kinds of ideas. But Pythagoras definitely wasn't the first person to figure out the Pythagorean theorem, but certainly was one who kind of brought it to prominence. So I think in more modern times, there are people who are generally, who made particular contributions, like Cardano, for example, from 1500-ish, who was one of the big obsessions was solving equations, and particularly people had figured out how to solve quadratic equations with x squared and so on. That had been figured out back in antiquity, but equations with x cubed, people hadn't figured out how to do that. And that was I think I noticed on that website that there's an example about a method from 1000 AD for an Arab method for computing solutions to cubics, but the systematic kind of algebraic solution was figured out in the 1400s, and that was a big sort of was a big intrigue about who figured out the solution to the cubic, and there was a sort of big presentations at court about, you know, who can demonstrate that they can solve a cubic and so on. Cardano is the person sort of most remembered in history for that, partly because he wrote a book. Cardano was another colorful character. Today's world, he's the Cardano cryptocurrency is named after that Cardano. But Cardano was the person who, in solving the cubic, to solve that mathematical problem, he invented essentially a bunch of mathematical technology. And two pieces of mathematical technology, which strangely were sort of invented at the same time, which were take negative numbers seriously and have imaginary numbers, numbers like the square root of -1, I, and so on. Those two things were both introduced by Cardano in his Ars Magna book, among other places, at that time. But that was a sort of a point contribution, but one that's significant to, it's worth realizing in the history of mathematics, a lot of things like, for example, decimal numbers, those didn't exist until the 1600s. They were the idea of writing out, 1 point, blah, 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 didn't exist in that form until the 1600s, although there had been precursors to that in Babylon, but those were done in a somewhat different way, and so on, with a longer story. But anyway, you're asking about mathematicians. I mean, I think that there are mathematicians who left big kind of, Euler, Leonhard Euler, and then Carl Friedrich Gauss, those in the 1700s and the 1800s, respectively. Those are two mathematicians who are particularly notable for having just contributed just a very large volume of different kinds of mathematics that has survived and become important today. There have certainly been in the history of mathematics, there have been people who've solved problems that have been existed for a long time. There have been people who've had very insightful particular ideas which have kind of unlocked whole directions of mathematics. There are mathematicians who seem to do things that are kind of like magic. A famous example of that would be Srinivasa Ramanujan, who was a person involved with number theory, who was Indian mathematician who invented just a huge number of bizarre formulas, like e to the pi square root of 163 is roughly an integer, and he noticed that and then realized, oh, you could use things like that to approximate pi, and for a long time that was the best method for finding approximations to pi. But Ramanujan was interesting, perhaps for modern times, because he wrote down all these formulas and they just seemed like bizarre magical kinds of formulas. And I think I wrote something about Ramanujan a few years ago. Let me see, I can probably pull up a couple of his formulas just for fun. He was, what was interesting about those formulas, let me see here. Where is it? Oh, here we go. Yeah, I wrote this in connection with a movie that came out about Ramanujan. Let's see here. This. Let's see if I have some examples here. Oh yeah, this is some of Ramanujan's writing. So in 1913, Ramanujan sent a letter to that time he was working as a shipping clerk in Madras, now Chennai. In those days, he was a human computer, a person who was did lots of calculations with numbers, but he also was trying to figure out math. And he wrote down all these strange formulas, and just pages and pages of very strange formulas. This is the letter that he sent. It just has all these mathematical formulas. And these seemed like kind of magical formulas. It's like, how on earth would somebody know this is a continued fraction that adds up to this weird thing here? And how did he figure all this stuff out? Well, I think the answer is that he did something which is very similar to what we might do today. He was really good at just calculating things with numbers. It's kind of what he did for a living, among other things. And so he would work out. He would work out kind of these things. He would figure out that if you summed up this series a certain distance, you got roughly this number. Oh, then he could figure out. He had good intuition for what the final result would actually be. And so when he didn't have kind of a proof in the Euclid sense about what the results would be, but he had a really good intuition for what the likely forms that would come out would be, and he then checked them numerically. And so when he found out from G.H. Hardy, the mathematician he sent this stuff to, who was a very stiff kind of fellow in many ways, when he found out, where Hardy was like, how did you prove this? Because that was the only way that Hardy knew to do mathematics. And Ramanujan would make up things like, it came to me in a dream and so on. But I think the reality was he was a very, very good calculator and had very good intuition about how results would come out. And he didn't really know, in the sense of Euclid-style proof, that the results were correct. And in fact, he was then very surprised and pleased when Hardy said, oh, I can prove that result. In fact, Ramanujan came up with some results about primes that turned out not to be correct, although the disproof of those results was something far, far beyond, involved numbers much bigger than any that, much larger numbers of primes than Ramanujan could possibly compute. All right, I think, yeah, the movie that this is, that I was commenting on here was The Man Who Knew Infinity, after the book by the same name. All right, well, I think we should wrap up there. So thanks for joining us. And if you, I encourage you, if you want to see a physicalized version of these artifacts of the history of mathematics, support Museum of Mathematics, and help turn these things into kind of a physically real kind of thing. So thank you very much, and